Okay, thank you all for joining. Thank you to AltLayer for putting this on. I'm Robert Miller. I'm Steward and Product Lead at Flashbots. I'm going to be talking to you today about where rollups go from here, so what the major large design decisions they could make are, and kind of the MEV perspective on these design decisions. So in any conversation about what rollups should do, where they should go, we need to start by setting context in what we're talking about. There's two major parts of a rollup sequencer that we're going to be discussing today. One is ordering, so how transactions in an L2 block are ordered. The second category is proposing and pre-confs. These are separate things, but they are so intertwined, and the design decisions that you make about them are so related that I grouped them into one category. And this is how you decide what an L2 block is and how that gets to L1. So if a server is just giving you pre-confirmations, we'll eventually post it, or maybe you need some external consensus. So these are our two categories, and we'll go over the major design decisions in both categories and talk through what we think rollups should do. In any conversation about that, we should begin with what the goals of a sequencer are. I listed 5 here. UX, you want reliable, fast transactions for users. You want throughput, so being able to do a lot of compute. DevX is also really important, getting new types of applications, not just the ones that exist today. Revenue, maybe a secondary consideration to people who are trying to grow the pie, but still important. And of course, decentralization is the reason why we're doing this at all. And so given these design goals and our two big categories of ordering and proposing and pre-comps, what are the choices that people could make? There are a lot of different decisions to make in both of these categories. So how you order transactions on an L2, you could do something like PBS, like L1, where you separate out the party that proposes blocks from who builds it. You could have a public mempool, a private mempool. You could order things first come, first serve. We'll talk about how to think about these different choices and make some concrete recommendations on them. And in proposing and pre-comps, I really like this framework that Vitalik laid out in a recent blog post of 3 major strategies that a rollup could pursue today, which is 1, being based, relying on the Ethereum base layer for your sequencing. 2, proudly being a server with pre-confs and blockchain scaffolding. 3, a compromise approach between those two where you have a committee, so you're more decentralized than a server, but you are less decentralized than being based. And we'll talk through that at more length in a bit. So we'll start with ordering, how transactions are ordered in L2 blocks. How should you think about this as a rollup and as a sequencer? The backdrop to this is that rollups are trying to scale right now. So these two graphs show how rollups are trying to scale, and successfully so, both supply of their block space and demand from users and new types of applications. This is pulled from It's Time to Talk About L2 MEV, a recent blog post from Danning on the Flashbots team, which is phenomenal. These two graphs if you're interested in seeing them more. So on the bottom left, you see how the average gas fee for a transaction on rollups dropped significantly after the Forward 4.4 upgrade. And on the bottom right, you see how when costs went down after Forward 4.4, the transactions per day went up on these rollups. So we're scaling both demand and supply. And this context really matters because there's actually quite a bit of money at stake from MEV that can be made on these rollups already. And so this graph is the volume of naive atomic arbitrage that we can measure on rollups. And if you can't see there, the volume in the winter months of this last year got up to hundreds of millions of dollars annually. And so this is the volume of the trades, it's not the total profit, but from this we can infer that there are tens of millions of dollars of MEV in just naive atomic arbitrage that are available and being captured today already. So there's a lot of money at stake in how these rollups and their block space markets work. And there's a lot of incentive to find a strategy that works for extracting MEV. And that really matters because that incentive means that searchers and people who are trying to extract MEV will find every single edge possible to do so. And how you create and allocate block space informs the dominant MEV extraction strategy that searchers will use. And then that strategy, depending on what it is, will carry with it different negative externalities. So you want to choose a very thoughtful market mechanism for how you create and allocate block space in order to minimize the negative effects that come from searchers trying to extract MEV on your chains. And again, there's hundreds of millions of dollars every single year that are extracted this way. And so there is a large financial incentive to figure out the dominant market strategy here. And one takeaway that I want you to have from this presentation is that if you don't make an efficient off-chain auction, then the auction is going to happen on-chain instead. And that's sort of the big takeaway from the ordering section, and I'll explain this in one level more of depth. So what I mean is that in the presence of low fees, if you have an inefficient market, the dominant strategy is to implement your MEV extraction in a smart contract and just hammer the chain. Spam it as hard as you can. And that's because you can make money by having 1,000 cheap reverting transactions that fail to extract any MEV, so long as you make a single successful MEV extraction transaction. So you'll implement a smart contract that looks for ARBs on chain, and you'll eat 1,000 transactions that fail at 1/100th of a cent in order to make one ARB probabilistically that makes $10,000 or something like that. Those are sort of the economics that we're talking about. And this graph shows this in practice, where if you look at bot contracts on Base, they have a way higher revert rate than other types of transactions. As we can actually infer that this behavior is going on in practice in the real world. And the reason is that on these L2s, you have a private mempool by default, and so there's no signal of when there's going to be an arbitrage transaction or not. And instead, you just have to guess when that's going to take place, and you send many different transactions and probabilistically guess one of them is going to land behind the right transaction that creates an ARB opportunity. And this is bad for rollups because it wastes gas that could go to real users. We might scale these things to 1 billion gas per second, and then 999 million of it could be used by people trying to find ARBs on chain that don't actually create any economic activity. They all fail and revert. It's wasted storage and compute from nodes, because every single one of these ARBs that is trying to find an arbitrage on chain needs to be replayed as a part of a full node in perpetuity. You're storing it. It's extra load on the sequencers, and we've seen bursts of MEV activity actually bringing sequencers down, and so it could actually cause downtime. And because it's inefficient and it leaks value to MEV searchers, it's lost revenue too. And again, we're talking about hundreds of millions of dollars a year here. And so what do we do about this? Well, how Flashbots address this on L1 is by having a sealed bid, first price auction, where failed bids don't get included, and it's facilitated by this off-chain actor. And the result of this is that you have this really efficient auction for block space that maximizes revenue for the sequencer, and it frees up gas by keeping reverts of things that don't actually produce any value off-chain through this failed bid protection. And furthermore, you get front-running protection with the sealed bid auction too. This is how we solved it on L1, or at least created a more efficient market structure, although that is still evolving on L1. And what I also want to get across to you is you don't need to copy exactly what happened on L1 too. And so just by having an efficient auction doesn't mean that you need front running as well. You can still have front running protection. And one thing that we're really excited about at Flashbots is using trusted execution environments to provide users both this really efficient block space auction and front running protection. And so if you use a block builder inside of a TEE, you get an encrypted mempool out of the box in addition to this more efficient mechanism for allocating block space. And so that's the ordering section, what we should do for rollups and how they order their transactions. The TLDR, again, is that you need to run an efficient off-chain auction. And then if you don't do that, you're going to get on-chain spam instead. Okay, so we talked about ordering. Let's talk about proposing and pre-confirmations now. So how you decide on an L2 block and how that L2 block gets to L1 as well. I'm relying on these L2 strategies from a great blog post that Vitalik laid out. You should really read it if you haven't already. He lays out 3 different possible endgames for rollups. And so one is to be based both technologically and spiritually. That means that rollups become sort of shards of Ethereum. They optimize for being conduits, pass-through conduits for Ethereum, and its base layer, its decentralization, its censorship resistance. The second polar opposite of this strategy is to be a proud server with blockchain scaffolding. This means a much more centralized approach, but you constrain that centralization by having proofs on what the sequencer's behavior is and making sure that it's following the right rules. And the middle compromise approach between this very decentralized, very centralized approach is being a 100-node fast chain, so you have some level of decentralization, but it's certainly not the same as Ethereum. So we'll walk through each of these different strategies and talk a little bit about what makes sense or not, and then what rollups should do from there. So based rollups, relying on Justin Drake's description here, again, it is when a rollup and their sequencing is driven by the L1 proposer. I don't have all that much to say here other than it only really makes sense if you have fast block times or pre-confirmations, because if L1 is driving your sequencing in independent of pre-confirmations or faster block times, your rollups block times are the same as Ethereum, and users do not want 12-second block times when they're used to 1 or 2. So this makes sense so long as you have fast block times or pre-confs. Being a server with blockchain scaffolding also can make sense. If you're really optimizing for performance and some types of UX, it makes sense to centralize things a little bit more. Then you layer on proofs to constrain and enforce behaviors that you want. It's sort of roughly where most rollups are today. A lot of them are just single servers, but we rely on ZK proofs or fraud proofs. And this is also probably fine in the long run if that is what you're optimizing for. Those are your goals. The compromise approach also sort of makes sense. There are some places where you don't want to be based, but you still don't want a single server, single party that controls the sequencer, and so you distribute that over a couple parties. You lose some efficiency here because that's the cost of decentralization, and it's kind of what Vitalik in this quote here thinks is the de facto roadmap of many L2 projects at the moment, and this also makes sense. And so my path to choose for everybody is sort of, it depends on what your goals are. If you really care about performance, you probably want to be a proud server constrained by proofs. But it's also very reasonable to align with the Ethereum base layer as well. So it depends on what your goals are. But we can say something on what the next step of rollups are, and I have a concrete sort of recommendation to make to rollups. So almost all rollups today are servers with blockchain scaffoldings. They're the single sequencer. Most rollups are still trying to figure out what their end game is, so where they fall on those 3 different strategies that Vitalik wrote, and they don't want to do anything that impedes on either performance or their compatibility with that end game. And so how do we iterate from the status quo? How do we improve being a server with blockchain scaffolding today while still meeting these criteria? My modest proposal is to put your centralized sequencer in a trusted execution environment. And so this is a piece of hardware that gives you both privacy as well as tamper-proof guarantees on your code, which is really interesting because that integrity that you get, because it is tamper-proof, means that you can implement fast, secure pre-confirmations, much more secure than either a centralized server giving you a promise, more secure than economic stake in many cases. You can also implement TE proofs on top of that, so you go from single proof to multi-prover. It's very interesting. While still being compatible with any of the 3 endgame strategies, you can still iterate to be based, you can still be a server with blockchain scaffolding, you can still distribute to 100 nodes. And it is synergistic with block space auctions for MEV, because like I said, you need this auction with privacy, and an encrypted mempool is really nice for front-running protection. Finally, you don't compromise at all on throughput here, and so you sort of strictly get better guarantees with almost no performance hit. We are running a mainnet block builder on Ethereum, which is one piece of infrastructure that has the highest performance needs of anything in crypto. We're running that right now, and it is comparable in performance to our non-TE builder. And so my message here is sort of, no matter what your plan is in the future for your rollup, as a next iterative step, we think it makes sense to put your sequencer inside of a TEE. And we can check what these prescriptions are against our goals from the beginning, and so putting your sequencer with an auction in a TEE against our 5 goals makes a lot of sense. So the UX, you have a private mempool, you don't get front running, you get a bunch of interesting new features like new transaction types, new apps. You have no performance loss. It may actually make your chain even more performant because you no longer have this on-chain spam. Your TEEs can act as coprocessors too, which we didn't talk about that much, but I'll throw that out there on DevX. You get more revenue from the efficient auction that you've made, and it constrains the sequencer and improves its guarantees relative to today because the TE can't lie to you about pre-confirmations, as an example, and you have multi-proofs too. And so it even helps with decentralization. So we think this is really a home run with few downsides here. The big downside being you need to trust the manufacturer of the hardware of the TE. And so in summary, we think that all three pre-conf and proposing strategies are viable. It sort of depends on what your goals are to do in the long run. But for ordering, you specifically want an off-chain auction that is efficient, because if you don't have this off-chain auction, you're going to have on-chain auctions and spam instead. That's going to clog up your block space. And in the short term, we prescribe that off-chain auction for ordering and putting sequencers in TEEs. So that's my talk. Thank you for listening. If you're excited about this, please come and talk to me. Thank you.